So this video is one of the most important videos you're going to watch for this entire course. It tries to wrap together a whole bunch of concepts that we've been learning so far and really focus on a much more theoretical approach of being able to build some equivalencies between all of these statements that you kind of see here on in this picture. So this theorem is from 2.3 in the textbook, which covers characterizations of invertible matrices. And the idea is that this theorem basically lists out a bunch of statements that are all what we call equivalent, which means that if one of these things is true, then they're all true. And if one of these things is false, then none of them are true. So for instance, if I can show that I have an invertible matrix, I immediately get all of these for free. Or if I can show, for instance, that AX equals 0 has only the trivial solution, I get all of these for free, etc., etc. So again, what we're going to try and do, the purpose of this video is to tie together a bunch of ideas that have probably seemed like we're just kind of learning them one after the other, but they're all super closely connected. And at the end of this video, you need to study it and essentially try and build some flexibility and fluidity in the way that you think about these particular topics. So what I'm going to do is I'm just going to start with one of them and kind of show you how all the rest of them have to also be true. So for instance, I'm going to start with showing that if we have a matrix A and the columns form a linearly independent set, what information do we get from that? So let's pretend, again, I'm going to show via example, not by a rigorous proof, but I'm going to show via example. Let's pretend that we have a 3x3 matrix whose columns are linearly independent. Okay. Now I'm claiming these are linearly independent, and remember that knowing whether three vectors are linearly independent is not as simple as just showing that these are not multiples of each other. You have to actually try and row reduce this thing. And that actually brings us to the first equivalency, which is like, okay, if these vectors are linearly independent, you may remember from work that we've done earlier, if we try to solve AX equals 0, right? If these are linearly independent, then this has to can only have the solution, what we call the trivial solution. It can only have the solution x is equal to the 0 vector itself. Now, why is that? Well, if I label this vector v1, v2, and v3, right? These columns of A is what we're talking about here. Then solving the equation ax equals 0, remember that x is here, has our x1, x2, x3. Solving this really just boils down to trying to solve the equation x1 v1 plus x2 v2 plus x3 v3 is equal to the 0 vector. And if you watched my video, the week 3 extra video that I posted at the kind of beginning of this week, you'll notice that if you try and solve this, you can rewrite it as x1 v1 plus x2 v2 is equal to negative x3 v3, and then I could divide everything by this negative x3 right here and create a brand new x1 v1 plus a new x2 v2 equals v3. And the idea is that if this thing has a non-trivial solution, what you're telling me is that there is some x1, some x2, and some x3 that'll make this true. But that can't happen, because if that's true, then this is also true. But that would mean that v3 is what? With respect to these two vectors, it is a linear combination of those two vectors, which goes against our original claim that the columns of the vector or of the matrix A are linearly independent. So that gives us a few things from this chart. We've now shown that AX equals 0 has only the trivial solution, that the columns of A form a linearly independent set. That was the thing that we kind of just started with. So the fact that this can only have the trivial solution means that if I create the augmented matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I try and solve for this, what should I get? Well, eventually through some work, we would eventually row reduce this thing down into row reduced echelon form. And in order to get the trivial solution, this is the matrix we would have to get. So in order to do this, that means that the matrix A, this matrix here, is what we call row equivalent to the identity matrix. And all that means, row equivalent, this is a topic I brought up in the very first week of class, but it's been a little while. Row equivalent matrices exist when you can take one matrix and you can do any of the standard row operations and turn it into the identity matrix. I take that back. Row equivalent is just like you do an operation to it and you get a new matrix, and then those two matrices are considered to be row equivalent. We are interested in the case where A is row equivalent to the n by n identity matrix. And that has to happen in order for us to be able to solve AX equals 0 and only get the trivial solution x equals 0. So from that, we immediately get A is row equivalent to the n by n identity matrix. That immediately gives you n pivot positions because A is an n by n matrix, in this case a 3 by 3, so we would expect to have 3 pivots here. Okay, so let's see, where else do we want to go? So immediately I'm drawn to the fact that I'm drawn to H, right? The columns of A span Rn. That should make sense because in the last couple of homeworks we've talked about, we've brought up the idea that if this is a 3 by 3 matrix, then these columns here are 3D vectors. Those are 3D vectors. And those 3D vectors, how many of them do you need to span all of R3? Well, you can't do it with just 2 of them because 2 of those vectors gives you just a plane in R3, some random plane. You need 3 linearly independent vectors, but we started off with the idea that those are 3 linearly independent vectors. So of course this is going to span R3, and likewise if you had n number of those linearly independent vectors, they would span Rn. Okay, let's see, what else? The equation, let's see, a linear transformation x is 1 to 1. The equation ax equals b has at least one solution for each b in Rn. Let's tackle the 1 to 1 bit because this is covered in the last video that I talked about. So this is a direct result from ax equaling 0 having only the trivial solution. And remember that 1 to 1, if I draw a picture, right, of our domain and our codomain, if I take some x1 vector, x2, right, these are the solutions to this little transformation here. And I pretend that there's some vector b over here, okay? Then 1 to 1 says that if b came from somewhere, it can come from at most one place. So the idea is that, can this happen under this particular transformation? And the answer is no, because what you're doing is you're then telling me that there are 2 sets of x1, x2s, and x3s. Remember that this right here is it's an abusive notation, sorry, but this, has its own little set of solutions, and this right here has its own different set of solutions. And you're telling me that 2 sets of solutions can get me the same vector, but we just talked about how that can't possibly happen because of this work right here, right? You can't, if I could have 2 different sets of solutions that give me the same vector, that would mean that my input column vectors, these guys up here, are linearly dependent, right? But you can't do that because they're linearly independent. So we immediately get, right, we immediately are going to get that the only possibility is for this transformation to be 1 to 1. So this linear transformation that's defined by the vector x going is mapped to ax, that's given to us 1 to 1, perfect. Let's see. The equation, let's look at this, onto Rn. Okay, so the linear transformation is an onto transformation. That also makes sense. Again, remember that onto means that every single vector b that exists in our codomain has to have come from somewhere, right? It has to have come from some input vector, but that is literally the definition of these 3 vectors spanning all of R3, right? If you span the entire space, that means that these vectors can get you any vector in R3, that we can add them together in some ways and get any vector in R3. that immediately means that we are, since this is a 3x3 matrix, we're going to R3, so we are obviously mapping onto R3. And that kind of gives us this one, right? The equation AX equals B is going to have at least one solution. There's going to be some sort of solution that we get for free once we verified that this is onto. So the only one we haven't really talked about yet is invertibility. And if you remember from like algebra or pre-calculus, a function only has an inverse if it is one-to-one and if it is onto. And we have succeeded in showing both of those things. And so in the same way, A is an invertible matrix. It's an n by n invertible matrix. And so this gives us that A inverse exists, which is going to be really good for us. And you'll notice that our matrix A kind of satisfies the criteria that we were interested in before. It has to be a square matrix. It can't be a 2x3 or a 3x7 or something like that, right? It has to be a square matrix. And then the columns have to be linearly independent. We have to row reduce down to the identity matrix. All that good stuff that we learned about from before still has to hold true. If we cannot do this, if we cannot get the identity matrix, which is the process that we used in the last video where I was putting in the matrix A here and I over here, in order to get the inverse to show up, we had to be able to turn the left side into the identity matrix in order for the inverse to show up. If we can't do that, the inverse doesn't exist. So again, all these topics are kind of coming back and kind of interlacing and webbing and weaving together. So A inverse existing gives us these two as well. I'm not exactly sure why the textbook writes it like this, because this C here is just A inverse and this D here is just A inverse, right? It basically says there's an n by n matrix such that one of those things happens. That is A inverse. So I guess what it's saying is that if you have an n by n matrix and you find some matrix C such that this happens, then immediately you know that that an inverse exists. You immediately get all these other conditions, and then you also are immediately going to get this condition as well. It's a little weird. I'm not sure why they do that, but these two things are kind of obviously equivalent. The last one's kind of a little obscure in my opinion, but the transpose is also invertible. So what this means is if I take that matrix A and I flip it on its side, so all those rows become columns and the columns become rows, so 2, 5, 8, and 3, 6, 9, pulling from the work we did earlier, that all of these columns are also linearly independent, that we could row reduce it in the same way. You could imagine that if you take this and you turn it on its side, we still have a matrix that I could rearrange. I can just do some row operations and get the identity matrix, even if I rotate this 90 degrees and turn it on its side. So therefore, the transpose of A is also going to be invertible as well. So that's going to do it for this video. It's a pretty short video, but there's a lot of information jam-packed in here, like a lot. Like you have to understand what linear independence is. You have to understand and recognize the business behind linear combinations and talking about span and spanning an entire space versus spanning maybe a small piece of it, right? Like if you have two 3D vectors, you don't get all of R3. You only get some plane in R3. And talking about one-to-one and onto and the inverse existing and stuff like that. So I would suggest watching this video again, taking some notes, maybe coming up with some of your own examples, reading the textbook in 2.3 where it covers some of these and goes to the proofs. And then once you feel comfortable and you really feel like, okay, I feel comfortable talking about the columns of this matrix A as, the matrix A is a transformation. It could also be a system of equations. If we look at it horizontally, it could be a vector equation. Being able to solve this has to do with linear independence and linear dependence, and having n number of linearly independent vectors lets us span a space of a dimension n, all that good stuff. If you feel good with all those things and most of these things feel comfortable for you, then go on to the next video. And if not, just keep watching, read the book, post in the discussion, send me an email until it feels good, because we're going to kind of keep adding on to this theorem. This theorem is actually many bits longer, and it keeps going. There's a reason I've cut it off, because it keeps going and it talks about some other things which we're going to pick up in the next video.